Syzygy, episode 110, Euclid's 5 Big Questions. And welcome back to another edition of the Syzygy podcast. Emily, it's been a while.
It's been a summer.
It's been an entire summer. My name is Chris Stewart. I'm sitting here with Emily, the aforementioned Emily Brunsden, here around the table at the University of York, where we're surrounded by, outside your window, hundreds of thousands of prospective students and their parents wandering around because it's open day here. That's the season that we're in. It's the pre-return to university after the summer break, but we're not quite at the students moving in to campus yet. We're at the potential students coming, having a look around stage. What's going on out there?
Yeah, so these are the students who are not coming this year, of course, but who may come the next year.
Right.
So, yeah, in the UK,
No wonder they look so
we start
small.
them off early. Yeah.
It's adorable. They all look about 12.
Yeah.
And their parents all look so concerned and interested. Yeah, it's
Yeah,
lovely.
it's quite interesting, some of the conversations you overhear.
Yeah.
Yeah, I heard one saying, "Oh no, you're going to cook your own food." I was fairly impressed.
What? That's what Uber Eats is for, surely. No, it's all very adorable. Do you like this time of year?
I love it.
Had a bit of a break, and now the students are threatening to come back. Is that a good thing?
No, it's actually very good because everyone comes back with a sort of newfound enthusiasm. It's that beginning of the year time where you get to crack open the new pencil and the stationery smells really nice because it's all brand spanking new.
Do students do that anymore? I mean, I remember that, but
I do. So
it doesn't matter what the students do.
They can do what they want.
You get to open the new packet of pencils, which is really
Speaking
nice.
of which,
Emily's just showing me that she has started the brand new notebook, which is the Syzygy branded notebook.
Yes.
Which you too, dear listener, can purchase if you go to syzygy.fm and go and find our merch store. They are available there for a very low price. But yes, Emily, I got her a couple of the Syzygy notebooks. And we've started on the new one.
Yes, volume
Excellent.
3. This is of my notebook.
Excellent. That's very auspicious for episode 110. I like that a lot. So listen, we should probably get into it because it has been a while.
Do we
are
remember
aware
what we're
of this,
doing
listeners.
here?
Yeah, this is a podcast.
Yeah,
Remember
okay.
what those are?
Yeah,
podcast, and it's about astronomy.
Right.
And way back in episode 109, all those months ago, we answered a listener question, which was, how much energy is there in the universe? Do we even know? And I don't know that we actually got a hell of a lot of clarity on that. It was somewhere between...
Well, you're convinced it's 0.
Yeah, it was somewhere between an extraordinary amount and literally 0. So take your pick. But I don't know, there haven't been any updates on that since
I'm not
then?
aware of any energy being created since our last podcast.
No.
I mean, I think we would find out about that if that happened.
Yeah, I mean, entropy's gone up, but other than that...
Yeah.
So I think we can probably draw a line under that. So today we're talking about something brand new. Today we are talking about, well, it's not quite brand new. It sort of launched and lifted off a little while ago while we were on summer hiatus. But I think that's perfectly reasonable. It's still a very new thing, and that is the Euclid mission.
Yes.
Emily, what and who and how is Euclid? What are we talking about today?
Yeah, so Euclid is an ESA spacecraft that's been in development for quite a long time, and as these things do, tended to be the ins and outs and mergers of lots of different ideas and programs. But however, it's all come to a head, and we have a telescope that's been launched into space on the 1st of July 2023, and so far it works.
Excellent. And that's the TLDR, is we launched a new thing and it's working, which is fantastic. So we're going to delve into that today. It's always exciting to have a new bit of astronomical kit, particularly to have a new bit of astronomical kit in space. But before we do get onto that, I just wanted to quiz you a little bit about some of your summer adventures, because you went and checked out a bit of astronomical kit.
I did.
If I'm not incorrect. There's a certain bunch of mountains in a certain water-surrounded state of the United States of America, which has a bunch of kit up on top of it. Emily, what did you do? Where did you go?
Well, I went up a volcano to look at some telescopes.
As you do.
Yes, in Hawaii. So that was, it was absolutely fabulous. So I had a science conference there, which I went to. And on our little holiday that we tacked on to the end of the science conference, which was in Honolulu, we went to Big Island and drove up Mauna Kea to just visit, just to visit. We didn't even bother to pull any contacts and go and look inside, but we just looked at the wonderful domes and telescopes of the top of the mountain.
So what's up there? What's up on top of that?
Well,
There's a few,
some of the
there?
biggest ones in the world.
Yeah.
It's one of the most prestigious observational spots on Earth, which is weird because you wouldn't expect a small island in the middle of the Pacific to be a good place to put a telescope.
You wouldn't really. I mean, so I'm assuming it's simply because it's a part of America, and so it's fairly easy politically to do things. And B, it's really high, and so you're up above the clouds.
Yeah,
is that the point?
B is really
Right.
the key one here. So yeah, B is amazing, and it's also it climbs very, very quickly from sea level. So we went actually snorkeling off the beach off Hilo Beach in Big Island, and that morning, and then drove up to 4,200 meters that afternoon to visit the telescopes.
There's not many places you could do that. You
No.
can't do that in Chile, for example.
No, it's absolutely crazy. I couldn't quite get my head around it, going from under sea level to 4,000 meters above it in just a few hours.
Yeah, and that kind of altitude, like that's serious altitude. Like you would be feeling that physically.
Yeah. Well, we did stop part of the way up and do sort of acclimatize. Once you're above 3,000, then you can sort of do that and then carry on up. I'm quite lucky. I don't seem to get affected too much by altitude.
As long as you don't try to do anything too physical, running a marathon or anything like that.
Yeah, exactly. But yeah, there's some beautiful big instruments up there.
Did you get any good photos?
Oh, man, they're just stunning. Because not only are you on top of this volcano, so it's sort of a fairly small area of height, if that makes sense, but you are looking down and you're looking up to the cloud inversion, and just the distance from the top where you were to the cloud inversion was a kilometre or 2
Wow.
kilometres. So you already felt just massively high and a very steep sort of slope. And that was just to the top of the clouds, and then there was, more ground.
So that really
below
is
that.
the point, is we're up above all of that. We don't have to worry about
Yeah.
that with our telescopes. We can just point them up and see really nice things.
Amazing, yeah. And they're beautiful. Telescopes are beautiful, let's be honest, right?
It does look pretty good. It does look pretty good. Yeah.
So you had the sort of the red volcanic rock contrasted with the bright blue sky, contrasted with the white and silver domes. It was just...
Yeah. Sounds all right. Well, speaking of astronomical kit, let's get on to the topic du jour,
Yeah.
which is Euclid.
Yeah.
Euclid has launched.
Yes, it is.
Now, as with all big, impressive spaceborne telescope missions, this one's been a little while in the making. So why don't we start with what's the history of this? Where has this one come from?
Well, I didn't read too much into the deep, dark history because these things get quite complicated. But there are, of course, people whose entire careers go into developing these missions. I believe Euclid came from 2 ESA proposals, one which was called Dune and one which was called Space. And
Space.
they're both acronyms for things, probably very tortured acronyms. I'm not going to...
Space is not
Look them
trying
up
very
again.
hard. Though. A new space telescope. What would you call it? Space. That's a 4-year-old answer.
It's a great answer. though.
Spacey McSpace face.
Yeah,
but anyway.
exactly. Yeah.
Okay.
And it was in these rounds for calls for proposals and calls for missions. Actually, these two got sort of put together because they were kind of using similar equipment to look at similar things for slightly different reasons. But why not put it all together
Sure.
and get...
Have you guys met each other? You should get in a room and talk. Yeah.
Yeah. So these came through these ESA programs. I think the budget, this particular sort of group of projects is about 500 million euro, that kind of level of.
Okay.
So it's a big deal.
That's a lot of money. You
Yeah.
want to get this one right. So
Yeah.
what's the point? What is Euclid trying to do?
Right. Well, Euclid is... Let's go to the questions that Euclid wants to answer.
Okay.
Because I find this quite nice. There's 5 questions Euclid's going to answer. First of all, what's the structure and history of the cosmic web?
Cosmic web. Structure and history of the cosmic web.
Yeah.
Okay. And the cosmic web is that's kind of the largest scale structure of the universe. That's what we're talking about?
Yeah. So
Right.
what is the distribution of matter in the universe on the biggest scale that you can imagine?
Okay. Ambitious.
Yeah,
Good.
sounds all right. That's question 1. What's dark matter?
Okay.
question 2.
We're not asking the small questions here.
No. There's only 5 of them, though.
You're getting a lot of bang for your 500 mil.
Yeah. How has the expansion of the universe changed over time?
Right. So this is getting into what? Dark energy, maybe. Now.
Well, you're
Or am I preempting?
You're preempting question 4.
Oh, geez. Okay.
What's dark energy?
So once we've answered the bit about how's the expansion changed over time, let's just cut right to the chase, which is and what's causing it. Good.
Yep. Oh, and last one, do we actually understand gravity?
I don't know. It kind of feels a little bit like you're burying the lead on that one, but sure. Okay. Why not?
Yeah.
Ambitious. I like an ambitious space program.
Oh, you got to.
Good.
I mean, if you're going to get funding, you got to ask the big question.
You do. And I think, like I said, for 500 million, that's a lot of money. You want to ask some big questions. They've done their job there. But the first thing you have to do before you can get to any of those things is actually get off the ground. And, the history of spaceflight is literally and figuratively littered with the remnants of things that didn't quite get off the ground. So this one worked.
It did work, yeah.
1st of July?
1st of July launch, yeah. Flung its way to L2, which is one of our favourite telescope locations.
So remind us again, L2 is one of the Lagrange points?
Yep, Lagrangian points. So this is a special point in space where the combined gravitational pull from the sun, the Earth, means that you can have this lovely stable orbit. So it's if you imagine in a line, then you've got sun, Earth, Lagrangian point 2. So it's after the Earth, if that makes going outwards.
Further out.
But because of the gravity of the Earth and the sun together, it actually travels at the same speed as the Earth going around the sun.
Yeah, it's a little bit counterintuitive because the Earth is pulling it in the direction of the Earth, which is towards the sun as well. And the sun's pulling it. So it sounds like that shouldn't be stable. That should just fall towards the Earth and towards the sun, surely. But because the further out you go, you need a bit more gravity and a bit more speed in order to keep you going in orbit anyway. But this combination of the Earth and the sun not only keeps it in orbit around the sun, but it keeps it in step with the Earth, which is what you wouldn't expect. It's not obvious that you can even have something that is going around in the same, period as the Earth, same orbital period, but further out. Yeah. That normally wouldn't happen.
It normally wouldn't. But as you said, basically the gravity from the Earth kind of tugs it along, pulls it, keeps it going so that it can stay close to the Earth.
Yeah. And it's one of, are there 5 Lagrangian points?
Yeah.
Again, a bunch of which aren't intuitive at all. You sort of look at them and think, that shouldn't work. But they're these curiously stable points which allow us to put things into space in these stable places. And they go around the sun with the Earth in interesting ways. And why would you put something at L2 and not, for example, just in orbit?
So you're getting away from the Earth, so you're not subject to, in some cases, the communication problems that we've littered our, low Earth orbits with.
Because there's a lot of stuff up there.
Lots of stuff, yeah. Earth shine is a big problem if you're close to the Earth as well.
As in literally the light coming from or bouncing off the Earth.
Bouncing off the Earth. Right. The Earth is actually quite bright, so light-wise. So it's nice to get somewhere a bit darker, but cooler so that you don't have to deal with all those problems.
How much further out is L2? Like, say, in comparison to the moon? Is it?
It's much further than the moon.
Much further than the moon. Yeah. So we're talking a really long way.
Yeah.
Okay.
It takes a while to get there. So it took Euclid about a month to get there.
Okay.
Yeah.
Given that it takes, a couple of days to get to the moon. Yeah, a month's a long way.
Yeah. And it's worth noting at this point that, of course, the telescopes are not actually on this little point.
Well, because there's more than one.
Well,
right,
indeed, it's quite crowded out there at L2.
Yeah. I mean, so they're all sort of fighting. No, it's my turn.
Yeah.
No. Well, so it's not a point in space.
Well, the Lagrangian point is a point.
Okay.
But what we do with the telescopes is we get them to orbit that point.
Right. So it's a little stable spot in space where you can sort of orbit around so you just have to make sure that everyone's nice and balanced out there. You haven't got too many things jockeying for position.
Well, indeed. So Euclid's got some good friends out there. JWST is out there. Gaia's out there. Kepler's out there. Not that Kepler's doing much, but
But it is
everyone's there. Yeah.
It's kind of nice to think of them all out there, kind of hanging out. There's a little welcome party for Euclid getting out there. That's cool.
Come on, join it.
Yeah. We'll make you feel at home. That's nice.
So that's where you.
So that's all, and that's all worked. I mean, it launched on the 1st of July. I was a bit busy on the 1st of July, so I wasn't paying much attention. I was over in Australia doing a lot of stuff. Hello to all of my Australian colleagues who were stressed with me. And you were doing other stuff as well?
Yes.
So neither of us actually, did you watch the launch of this one?
No.
I didn't watch the launch of this one.
And it was also a Saturday, so I was trying to, get my extra couple of hours sleep that I'm permitted on a Saturday.
You had other stuff going on. Yeah. But it took off, which is good.
Yeah.
And it went through all of the important things it's got to do, like get out of the atmosphere and then get out to L2, which is a long way. And everything's going fine?
Well, yeah, mostly. There's a couple of little things which we'll come back to that we're still we're still finishing commissioning effectively and getting everything up and running.
Yeah. But, I remember when we were talking about JWST, and there was a very long period of let's really carefully unfold all the bits and make sure that things are pointing in the right direction. And do we have all the communications up and running? It was a really long period of commissioning and testing, and let's not get too excited. But then when the first images finally came through, everyone went, oh my God, this is awesome. So where are we at with Euclid in that regard?
Well, commissioning started, and there's a little bit of a hiccup in what we call what is called the fine guidance sensor. So
it sounds important.
Well, it is. It's not cataclysmically something that's not working.
Right. It's not the course guidance sense. It's not the thing that's going to fling it into Jupiter or something.
No. So Euclid's a mission which we need to come back to and to see what it's actually doing, but it's pointing in lots of different directions in the sky. And as part of that, you need to know or be able to say, go here, and the telescope points here. And so there's lots of systems that will tell the telescope where it actually is oriented in 3D space and tell it how to get and point exactly where you want it to point. Part of that relies on stars, for example, to guide you around. And the fine guidance system is as it suggests, the very fine part of that. And so at the moment, there seems to be intermittent problems with that, where its telescope's not quite pointing exactly where you want it to every single time. But as of recording, it sounds like they might have a fix in the software to sort it out, and they're going to try test it on the ground first to make sure that it's all works, and then if it works, they'll upload it to the telescope, and fingers crossed it's all
Give
good.
It a go. Because, pointing in the right direction is kind of like, that is the one job.
It's quite important.
That's the thing you want your telescope to do. That's not optional.
No.
That's
there is some bits
critical.
you can kind of do. There's always mitigation, but so the telescope's continuing on doing other performance verification, or just checking that it operates as expected as much as it can without this particular system in place. And then when that hopefully very soon gets uploaded and tested, then we should be good.
Fingers crossed. Okay. So we should, I guess, probably talk about what the hell is this thing trying to do?
Yeah.
So you went through its 5 big questions.
Yes, yeah.
But that doesn't really tell us how.
No.
So how? What is Euclid? Emily?
Well, I started this journey by looking up Euclid, and I got to the ancient Greek mathematician page.
Right. Yes. The Wikipedia disambiguation? Is that the word? Disambiguation page?
That's the one, yeah. So I went down a little bit of a rabbit hole with Euclid the mathematician, because this is quite interesting. I quite like a little bit of ancient history, and
Those of you listeners who are actually champing at the bit to go, yes, but what does the bloody space telescope do? We'll get there. Don't worry. We'll get there. Have a listen to the history of mathematics.
Honestly, it is relevant. I will promise you that you will learn something relevant at the end of this.
Never let it be said that we get to the point too quickly on this podcast. We like to take our time.
If you wanted the headline, it's going to find out what dark energy is, then you're fine.
Yeah.
That's what you need to know.
Yep.
Anyway, Euclid. So Euclid was an ancient Greek mathematician.
Yes.
Well, I guess he was a Greek mathematician a long time ago.
Yes. He might have been ancient as well. I don't know how long he lived for.
Well, no.
But the point is, we are talking, a couple of hundred BC?
About 300 BC-ish. Yeah. Nobody's quite sure. If you were into your kind of history of science, he's smudged somewhere in between Plato and Archimedes.
Okay.
In that chain of
sort of wedged in there.
Yeah, somewhere in there. He's very famous for geometry. Geometry was Euclid's thing, and we'll come back to that.
There's a whole bit of geometry named after him.
Indeed. Yeah. And we're going to find out why.
We will, yeah.
So his claim to fame largely rests on the fact he had a 13-book series, which was called Elements.
Elements. Not as in the periodic table, one imagines?
No, in, I guess, in the sense of elementary.
Right. Elements of what? Maths, geometry, elements of
Pretty much, yeah.
As far as they were concerned, elements of sort of reality of the universe.
Natural history of life. Yeah, it's all quite interesting. I think you had to be around at 300 BC to have the copyright on a book called Elements. I think. Yeah.
I think so.
I don't think
Has
you
anyone
get
got
away
this
with
one
it
yet?
today.
Oh, stamp that one. That one's mine.
So it seems like it's as with a lot of ancient history, I suspect it's not exactly clear which parts of these, because the books were sort of designed as a treatise of this is all the current knowledge of mathematics effectively up to this particular point in time.
Okay.
So it's not obvious which parts of that were necessarily coming from other sources and which parts Euclid did himself.
All right. I mean, the gathering together is impressive enough as it is, but yeah, how much of it did he sort of come up with himself and how much was just around in the ether?
It's impossible really to find out, I think, the details of that. But the quote that I quite liked, that I liked enough to write down in all its length and glory, was, apparently Euclid's achievement consists of assembling accepted mathematical knowledge in a cognate order and adding new proofs to fill in the gaps.
Right. Okay.
And that's from Marcus Asper.
I mean, this is a period of history when the idea of let's get a bunch of ideas and build on them in a very consistent, logically consistent way was really being explored.
Yeah.
And that's the basis for everything thereafter in mathematics and then eventually science.
Yeah, but it's clear Euclid wasn't just a collector of information. He was putting in bits to join bits of mathematics together. So he was inserting these proofs or these extra ideas and things. So he's obviously a genuine, talented mathematician in his own right as well. And he seems to have written these books in kind of the style of a textbook, which is quite interesting because that didn't necessarily exist as a concept before that.
So with really cheaply derived stock photography to begin each chapter and a bunch of questions at the end of each chapter, which are really annoying, get harder to go through.
Answers to the even numbered ones.
Exactly,
in the back.
yes, which are the ones that you never want the answer to. You always want the odd ones. Yes.
It's nice. It's interestingly also, here's a fun fact, probably the second most translated book into English.
The first being?
The Bible.
Well, I guess that makes sense.
It's an important book.
Yeah.
Very important. Now, the maths that comes into this book, there's a lot of geometry, there's a lot of number theory and things like that. But if you were to ask what's kind of the maths that we would recognise today, basically everything you learnt in maths at school before calculus is
right.
Effectively.
Okay. So all of the basic arithmetic, all of the basic geometry.
Things
stuff.
like this is a line. If you have 2 points and you draw a line between them, it will be straight.
Right.
Here's a triangle. If you add up the angles in the triangle, you will get to 180 degrees. Effectively, Pythagoras' theorem. That kind of
right. All of that stuff.
Yeah.
Yeah.
So whether you loved it or hated it, you can probably blame
you
Euclid.
You can thank Euclid. Thanks, mate.
That. Yeah. So this is important because this is now that just used to be called maths or geometry. That's what it was called because there didn't need to be any further information about
that's
labeling
it
than that.
Yeah.
Nowadays, it's called Euclidean geometry.
That implies that there are other geometries are available.
Other geometries are available, but the other geometries are fairly new. I say fairly. This is modern physics.
Well, in comparison to 200, 300 BC, it's new.
Yeah. So we're talking about stuff ideas that are coming forward mostly at the turn of last century, so early 1900s.
Right.
And our favourite Einstein's going to appear in this because this is when both from a theoretical perspective, but also starting to consider what observational fallout might be from these ideas. We're looking at, is flat the only geometry that's available?
Yeah, and that's, to be clear, when you're talking about things like in Euclidean geometry, you draw a line between 2 points, it's a straight line, and all triangles have internal angles of 180 degrees and so on. That's true for a flat plane. The really simple thing that you can do to show that that's not always true is on the surface of a sphere. Go and find a globe or a balloon or something. Draw yourself a triangle with straight lines along the surface of the balloon and then measure the angles between them. It's not going to be 180.
No.
You can have, go up turn 90 degrees, go along, turn 90 degrees, come back, turn 90 degrees, and you're back to where you started with. And that's not 180, but that's allowed on the surface of a sphere because it's not flat.
Yeah.
Get different rules.
And of course, spheres and 3D geometry existed. And that's not to say what the difference is the number of dimensions has to increase, because this is where our brains don't deal very well with the geometry. We live in the Euclidean geometry space. We think in Euclidean geometry. We operate in it because we operate in this 4-dimensional kind of space, or 3 spatial dimensions, 1 time dimension.
Yeah. And for the longest time, like, time's not even a dimension. It's just a thing that ticks away in the background.
No, not for us. It's kind of almost a different metric. But that's our perception of it. Now, if there existed further dimensions, then you can have these other geometries that exist within those further dimensions. And so that's why these things start to come in and start to become important.
Sure.
And it's in the construction of space-time particularly that we see this in astrophysics. So whether space-time, the fabric of the geometry of the universe itself, is Euclidean or not, is one of the fundamental questions that we want to know about our universe.
Yeah. I mean, the whole point of Einstein's and collaborators, colleagues' theories about space-time is that, I mean, you've got sort of global space-time and global geometry, and then you've got sort of local. And the whole point of Einstein's general theory of relativity is that you know, what's the phrase that mass tells space-time how to curve and space-time tells mass how to move. Mm-hmm. And that locally, for example, around something like a star, you've got the space-time warping, bending, and the Earth going around the sun as the Earth following a straight path, if you like, around the curved space-time around the sun. But that's sort of locally. Then you can ask the question globally, like across the universe. Forget about the little bits. What's the universe? Mm-hmm. Does it curve like a ball? Does it curve like a saddle? Is it completely flat? What is the geometry of the universe? And that's a whole other thing.
Well, the answer to that question is so profound that it affects the whole history of the universe from the very, very beginning to its very, very end. So Euclidean geometry is our interpretation of our local geometry is really, really important. What the global alternative to that might be is also very, very important.
So Euclid didn't have any sense that there were other potential universal geometries, but he did kind of codify what we understand about the Euclidean geometry of what we experience. So why is this mission called Euclid?
Well, I guess it stems from the Euclidean geometry, and the reason why Euclidean geometry is still at the forefront of our minds when we consider the universe is that, as we've mentioned, I think in a few of our podcasts, we're trying to measure this curvature of the universe. We want to see what the answer is. What is it? Which way is it curved? Is it curved? And every measurement, we get closer and closer to the answer, but we're getting closer and closer to the fact that it's so close to being flat that we can't distinguish whether there is a curvature. So is it, and there's questions about that, is that because it's so flat and where we are, we can't possibly see enough of the universe to determine that it is curved?
Isn't it weird that we've gone in a relatively short period of time, like within 100 years, probably considerably less, but let's call it within a century, we've gone from, what do you mean? Of course it's Euclidean. What other option is there? To, no. Euclidean would be so ridiculously unlikely out of all of the possible options for the curvature of space to, yeah, really seems to be Euclidean. And suddenly that becomes really quite, as you say, a profound question, because if it really does seem to be flat, why? Like, why should it be, given all the possibilities? So it is fascinating. So it's a nice choice of name. I give them a big tick for the choice of name.
So while Euclid in itself is not trying to measure the curvature of the universe, it's trying to address some of the big fundamental question marks that we have on the way to answering that. The biggest one, I think, is dark energy, because that has profound impact on how the universe evolves in its own right.
Yeah.
So,
and just reminding ourselves of dark energy, right? We kind of need to go back to the Nobel Prize winning research from the late 90s of
97.
measuring supernovae and basically using them to figure out over distant scales how rapidly is the universe expanding, and coming to the startling realization that the universe is expanding. We've known that for a very long time, but that it seems to be speeding up, and that the further out you look, the faster and faster things seem to be moving away from us, as opposed to the other way around.
It's very weird.
Very, very odd. And so that introduced the concept of, well, something must be causing that, right? Something must be making the universe's expansion speed up, which is not what you'd expect. And so let's give that a name. There's some kind of force mechanism stuff. I don't know. Let's call it dark energy and put that in a box over on the side, and we'll figure that one out later. And so far, theoretically, there's a few ideas, but no one's really nailed that one down yet.
No, although we are summarising this in a very succinct little way, effectively that is all we know about dark. We're not hiding things from you here with our grand theories and all the little hints of what we have of what dark energy. No, that is literally, we know that the universe is expanding faster than it should be, therefore dark energy. Everything else.
Yeah, there's a big ellipsis in the middle there. It's like ... therefore dark energy. I mean, at least for dark matter, we have no idea. We don't know what it is, but there are many competing thought. Like we could look over here. Maybe it's particles of this kind, or maybe it's big heavy But generally,
we've got more clues.
There's a sense that it's going to be little bits of stuff of some kind. It may be like ludicrously exotic stuff, or it might just be actually quite normal stuff that we just haven't looked at in the right way yet, but we think it's stuff. Dark energy, no idea. Is it fundamentally breaking the way we do physics? Or no idea. Haven't got the foggiest.
No.
Which is fun.
So it is interesting. And it's, so when you read up, what's Euclid going to do? It's going to look at dark energy and dark matter. It's very...
just those.
Yeah. It's very easy to almost see those two things as being, or just dark things. We're going to look at dark things. But those two concepts are so fundamentally different.
Yeah.
And our understanding of those two things are so fundamentally different. It's
almost a shame that they chose such similar nomenclature.
Yeah, I think
that they get put in the same box. Like, no, big crowbar separation of those.
Our journey to understanding dark matter is so much more advanced than to understanding dark energy.
And yet between the two of them, that's merely 95% of the known universe?
Yeah, something like that. Oops.
So again, ambitious, which you love. You love in a space program.
Yeah. Okay. Yeah. But let's then say how. Okay, you're going to do dark energy. You're going to do dark matter. You're going to do expansion of the universe, gravity, and the cosmic web.
So yeah, it's a long way from we have these grand goals, 5 questions we're going to answer. Great. How are you going to do that? Exactly?
Yeah. Well, actually,
put a thing into space.
Well, we put a telescope in space, and actually, you would almost expect this thing to be just covered, swarming in instruments.
Yeah, I'm imagining something which has got
and that and that and that. We're going to do that, and we got that sensor.
Telescopes pointing in all directions and big antennae and stuff. It's like no, it's not.
No, it's actually a really simple instrument. In fact, it's only got 2. Well, 3 if you sort of count one twice, instruments that are doing anything.
Okay. So that seems implausible for 5 quite extraordinary and, as mentioned, like diverse ambitions. So take us through it.
So, Euclid has effectively a visible camera, so it's taking images.
In the visible wavelengths.
Yeah.
Right, okay.
And we've even got, my computer screen's gone to sleep, unfortunately, but I did have up on the computer screen just before the first light images from this.
I'm going to bring
go wiggle my mouse. Go on.
Can I wiggle mouse? This is what people tune in for. Right, yes,
yeah.
So we have...
Let's just pretend that didn't happen.
Euclid early commissioning test images. Very nice.
Yeah, so you'll see on my computer screen.
Yes. Here's one I prepared earlier.
Yeah. Actually, on the left-hand side, this is the visible camera that's just basically taking really nice pictures.
Now, okay, on the left-hand side, and those of you who are using a device which allows you to see chapter art, you will be seeing this in real time during the podcast. That's a hell of an image, right? There's a lot in that.
Oh, yeah.
We're seeing lots of things.
Lots of things, mostly galaxies that you're seeing in that.
That's
Including
mostly galaxies.
That big smudgy one. Oh, yeah.
Well, the big smudgy one, obviously, but all the other bits are galaxies
Not
too.
all of them, but most are galaxies.
Is this a little bit like the
Hubble Ultra Deep Field?
Hubble ones where you can tell which are the stars because they're the big pointy ones?
Yes.
We have the same thing going on here?
Yes, we do, yeah.
So all the things that aren't big, bright and pointy are galaxies.
Yeah.
That's a lot of galaxies.
Yeah. So Euclid's looking
the
at
universe is
galaxies as its kind of bread and butter. And so by nature, therefore, that means you point out of the galaxy that we live in, the Milky Way.
Yeah.
You don't want to point towards the Milky Way band that goes through the sky because
that'd be
that's
a bit
full
pointless.
of stars.
Yeah,
That's our stars and our galaxy.
Yeah. So
they're
we're
not going to
pointing
help us
out
with these
of the
questions.
galaxy, between the stars.
Yeah, away from
away
the center of our
yeah,
galaxy.
okay.
Yeah,
And we're seeing lots and lots of galaxies, Emily.
Yeah,
that's an image that makes
there's
me
a few
feel very
stars,
small.
but loads of galaxies. Yeah,
Can I just point out this is an early commissioning image?
It is.
It's pretty good.
it's not bad.
pretty good.
If you look at a little bit detailed, so this we're talking about the black and white one on the left.
Yep.
There are quite a lot of image corrections, which will come. So there's lots of cosmic rays. Those are those little sharp streaks going through them. So, because what happens with CCDs is that with the pixels, they're triggered by photons and then they get electromagnetic signal through them. So just like a photon could hit a CCD and light it up, then a cosmic ray, which is a very high energy particle, can hit it and light it up. Now, we know we've been dealing with cosmic rays since the invention of the CCD. We know how to clean them up and get rid of them. They're fairly straightforward. But because these are very early images, these are just kind of like, whoa, this is us not even really dealing with all that kind of thing.
Right. So all of that needs to be cleaned up. But even given that, that's a hell of an image.
Not bad, is
it's pretty
it?
good.
It's not bad.
Pretty good. I mean, clearly it's working.
Yeah.
Right?
Yeah. So
Okay.
that's a visible camera. We've also got a infrared set, which is there's an infrared spectrometer. So that's the one that breaks up the light into its wavelength, so we can study exactly how much there is of each wavelength of light. And there's also a photometer, which is the image that you're seeing here. It's got a coloured filter effectively on it. So that's taking the same, it's not actually the same image in this case, but you could take the same images on the left in a coloured filter to see what the constituents, because white light is built up of all the colours.
Right.
So if you just want to see how much red is there in that white light, you put the filter in.
Okay, so that's the sort of thing that we're seeing in this second image. And again, you can see a bunch of stars, but everything else is galaxies.
There's a beautiful, beautiful spiral galaxy.
Okay,
There. It's
so
really cool.
we have a honking great camera or a couple of cameras, visible, and you said infrared. Okay, good, and they're working. Fine, great.
Yeah, and we've got a 1.2 meter mirror, so it's a decent sized collecting area. It's not quite as big as Hubble, but it's sensible.
It's big, but we're not out here to break size records. We're building something which is very specifically designed for purpose.
It is, and it's specifically designed to be looking at redshifts of galaxies.
Right. Okay.
So this is why we've got the infrared stuff, we've got the visible cameras as well. We're going to be looking at these galaxies and we're going to be measuring their redshifts.
Okay. And redshift, again, let's just remind ourselves, redshift being what?
Okay, so we got the Doppler effect, and that's what's happening is these galaxies are generally moving away from us. Because of the expansion of the universe, it means that there's more and more space being added in between us and a distant galaxy. So from our perspective, it looks like they're moving away from us, although the galaxy itself isn't moving. It's just there's more space-time existing in between us.
Yeah. I mean, the galaxy might be moving, but if you get far enough away, that random movement of the galaxy in itself is completely swamped by the fact that we've got all this extra space-time expanding between us and them, and that just pushes them further and further out. Yep. And so that's the moving away.
Yep.
And that means what?
That means that the light, as it moves away from us, just like a siren piece of sound, if you're listening to a siren and it's moving away from you, you hear the pitch go deeper.
Right.
As a galaxy moves away from us, the color of that galaxy becomes redder.
Redder.
Because the photons are stretched out to become redder.
Yeah.
Photons.
And you can measure that, the red shift against what you would expect the frequencies from the galaxy to be. And so that then tells you how fast it's moving away. And so that then tells you, by implication, how far away it is.
Yeah. And you can do things all sorts of ways round. So if you have a measure of the redshift, which is how fast it is moving away from you, and you make a separate measurement of how far away that galaxy is, then you can map basically the distance versus redshift.
Right. Okay.
To see that's how you would see the acceleration of the expansion of the universe, by saying, okay, we know the distances to all these galaxies. We know how fast they are moving away. Therefore, we can track that acceleration.
That makes sense. Yeah.
Yeah. So that's the addressing the expansion of the universe changing over time question, really. And a little bit the dark energy question too, looking at the change in the speed of expansion. They can do this. So Euclid's designed to do this out to a redshift of about 2.
Okay, and that translates
we like
as
using
what?
good units of redshift.
Yeah.
Very small numbers. It's just very deceptive. It translates to something like 10 billion light years, 10 billion years ago.
So that's quite a lot
in the universe.
That's quite a lot. That's encompassing quite a lot of the visible universe.
Now, alongside that, if you also do redshift, you can sort of do a slightly different calculation where you can use Hubble's law. Hubble's law is our mathematical description, effectively, for this idea that the further away an object is, the faster it's moving away from us. But you can use that in the other way around to get the distance to the galaxy, and you can use that to generate a 3D map of the universe, right? These are where all the galaxies are in relation to us. And so that's then starting to hit the question about the structure of the cosmic web.
Right. And so that's more concerned with a little bit less on how are these things moving, or how's the expansion relative to us, and more just placing them in space.
Yeah, making a 3D map
Right.
and saying what's the structure in that 3D map. Do we find more galaxies over here, or do they form in clumps and things like that?
And we've done this before, and there's some really interesting structure at those larger scales. Like, we know about local clusters of galaxies and so on. We have a bunch of galaxies which are around us here in the Milky Way, which form our local neighborhood. But on these vast scales, tell us a bit about the structure that we know already is there, and what we hope to get out of this one.
Yeah, so the reason why it's called cosmic web is because there seems to be this structure where you've got clumps of matter, and by clumps we mean massive superclusters of galaxies.
Like, we're talking huge amounts.
Yeah, not just 1 or 2 galaxies. We're talking about millions of galaxies will form a clump,
which is already boggling the mind. But anyway,
and then you get the next clump over, and there's some kind of stringy filament of galaxies all along the distance between those two, and then you have the next clump over.
And so it's like webs. I'm imagining sort of, that cotton wool stuff, or spiders' webs or whatever, just being stretched and drawn out with clumps of blobby stuff, but then these long filaments between them. Over vast
huge
distances.
Ones. I think sponge is probably a good example, because you sort of get the bubble, which is the void, and then the thin bits of the sponge, but where there's lots of bubbles that join together, you get clumpy bits of sponge.
And so what we do see on those massive distance scales is actually like quite serious, conglomerations of matter and huge voids with basically nothing in them.
Exactly. And that's not coincidence, right? If it was just random, you'd expect just random, just everything basically scattered randomly. But the fact there's this underlying structure, and there's something that's underneath all that, and what we think is underneath all that is dark matter. So the dark matter told the matter that we can see by its gravitational influence how to clump, and that then eventually evolved into galaxies and what we see today.
Right. And so by measuring that over the largest distance scales, measuring the distribution of these galaxies, measuring that cosmic web, that's what giving you information about the distribution of dark matter, which can then play into theories about what dark matter is?
Exactly, yeah. So we need to have mechanisms of dark matter forming these structures very, very quickly in the history of the universe. So that tells us some of the things that dark matter can and can't do.
Right. I guess if you've got a bunch of competing theories about what dark matter could be, it could be these weird particles or those weird particles or something else entirely. The thing about those theories is they need to be able to predict, okay, well, if it was this, then that would have this impact on what we can see. We can't see the dark matter, but this kind of thing would make the universe look like this. quick, astronomers, go and measure the universe. And so this might be a way of going, well, it's definitely not that one. It's not that kind of dark matter. And it's not that kind of dark matter, but it could be these kinds of dark matter. That's the hope.
Exactly.
Wow.
And it's how we, in the past, even ruled out some ideas of dark matter. I mean, you could hypothesize things like, well, maybe dark matter is just a whole bunch of planets that we couldn't see.
Yeah.
But planets weren't around before galaxies
Right.
to lay down the foundations of structure.
Yeah.
So,
like if this stuff is causing the large-scale structure of the universe, planets ain't going to be it.
no.
Right?
No.
Yeah, that makes sense.
Yeah. But on a smaller scale, Euclid is also designed to look at dark matter a bit more locally, perhaps, or in smaller doses.
So what, on the scale of like galaxies or clusters? Or?
Galaxy and galaxy clusters. And this is through gravitational lensing. So Euclid's also set up to look at how galaxies might be distorted because the light that leaves that galaxy might encounter some area of dark matter that we couldn't see along its way, traveling towards us, and that would distort the image that we see of that background galaxy.
Yeah, we've encountered lensing a couple of times in not the too distant past of this podcast. So refer back to previous episodes for a full description. But it's in the name. It's the lensing properties of gravity. If you have a bunch of gravitational stuff, matter of some kind, between you and something else, then that matter can act as a lens. It can bend the light around it and change or focus or otherwise do weird stuff with the image of that more distant thing. And so Euclid set up to look for that.
Yeah, and to take images of these galaxies that have been distorted by dark matter, and then after that we can unwind effectively the path of that light, and therefore predict not only how much dark matter there had to be to bend the light this way, but kind of how it's spatially located.
Right.
So what the structure
Right.
is
What
these
dark
scales.
matter would you have to have where in order to get the picture that we see?
Would you need like one blob here? Would you need one blob there, one blob there?
Right.
Whatever.
That sounds hard.
The maths is pretty interesting.
Yeah. Like this, that's not easy. That's not
Yeah,
simple.
no, it isn't. But it's something that we can do.
You're a clever bunch, aren't you?
I say we in the biggest, broadest
Look,
terms.
take the accolade
It's
when it
not
comes
something
your way.
I do on my
It's just,
weekends.
you know,
I'll admit to that. Yeah, so that's kind of the ways, and I think we've actually now covered the 5 questions.
So was that all the 5 things? Hang
Yeah.
on, let's tick them off again. What was number 1? Number
Structure
1 was
and history
structure.
of
Okay.
the cosmic web.
So we got that. The cosmic web we're looking at. Galaxies they're spread across space throughout all of space.
Yep.
Right? Okay, that's number 1.
Yep.
Number 2 was
Dark matter.
dark matter. Okay,
Yep.
and we're looking at that both from the cosmic web side of things, but also from the lensing
Yep.
side. Okay, that's tick.
Expansion of the universe and
Expansion of the
changing
universe.
over time.
So looking at redshift
Yep.
and how quickly are these things marching away from us, which tells us about how much the universe is expanding between us and them. Right? Okay.
Dark
tick.
energy.
Dark energy, which is related to that.
Yep, yep.
Okay. Tick.
And do we understand gravity?
Well, okay. How do we get that one?
Well,
I mean, that's just all of it put together.
I'm
isn't
going to
it?
hypothesize here. It is all of it put together, but I think you can also do things when you do start looking at the largest masses in the universe. So galaxies being, of course, the largest structures of mass, at least that are somewhat independent. So looking at how they behave and do they follow our current theories of gravity.
Right.
We do these tests in other ways as well. I mean, we've talked about, for example, watching stars orbiting the central supermassive black holes of our own galaxy,
Right. Yes.
subject to incredible
Yeah,
gravitational
doing stuff that stars were never designed to do,
yeah.
whipping around at ludicrous speeds. But what that allows you to do is go, okay, well, this is extreme gravity at extreme speed and extreme energy. And that's exactly what general relativity is all about. So let's test that.
So that's kind of the small, strong gravitational field tests. What I'm sort of extrapolating, if you like, from the rest of what we've talked about is that we're looking at gravity on these large-scale structures. You know, the fact that we had dark matter that might have laid down the gravitational structure of the universe that then all the galaxies kind of formed on.
Right.
I think it's that level.
So can you tease out from all of that information? We would expect everything we know about gravity to give us this pattern. Can we see even the slightest difference from that, which we could attribute not to dark matter or dark energy or anything else, but to actually gravity's doing something different? You know, physicists often do this sort of stuff, particularly in particle physics. You're always looking for that that tiny discrepancy from the thing that we know works really, really well at like the 99.999% level, but it's that 0.001% that contains all the juicy goodness, because that's where you'll find the new stuff.
We do spend quite a lot of our time trying to break our own understanding.
Well, because that's the fun part, right? Like if we understand it all, we'd all just go home and hand it over to the engineers to build stuff.
I think we've got a ways to go before we can even claim to understand the stuff. But
speaking broadly,
yeah,
I'm just saying.
It's good. No, it is very good.
So
yes.
Euclid's up there. It's doing its thing. We've clearly got a couple of pretty good-looking images coming off it, where we're off to a good start. You mentioned something earlier that it's not all working perfectly. And you said that there were a couple of issues perhaps with pointing exactly in the right direction all the time.
Yeah, that's all I had to say about that.
Right. It's a bit of adjusting we've got to do there. But otherwise, like, when are we expecting to get some real science out of this thing?
Well, maybe this is a good time to hit you with something that we haven't done for quite a while, I'm going to admit. How about a stat attack?
Oh, the infamous Emily Brunsden stat attack. Do it. Hit me with it.
All right. Are you going to guess the answers?
I'm going to try.
How long's the mission?
Oh, geez. I mean, you want it to be a reasonable period of time in order to justify its cost. So I'm going to say a decade.
6 years.
6 years?
But there's always,
rounded up
always
to the
option
decade.
for extension.
Yep. And let's face it, everything working well, they will extend it because, that's what happens. How long was Hubble supposed to go for?
Oh, not for a few months. I don't
weeks.
know. Yeah. How much of the sky is Euclid interested in?
Well,
fractionally,
okay. I'm guessing we're pointing up out of the plane of the galaxy. Mm-hmm. So at most we've got a hemisphere, right? I'm going to say it's considerably less than that. I'm going to say 10%.
It's about a third.
A third? Okay.
You can point up as well as down.
Oh, well, okay.
Earth's not in the way anymore.
Yeah, because the galaxy is relatively thin, right? Isn't it?
Yeah, you can point down and up. So it's about a third of the sky. It's going to cover.
Well, look, 10% is not that far off 33 1/3%. I think I'm doing quite well.
Not too bad. Yeah. How many sources is Euclid expected to...
Good Lord, I have no idea. I mean, I'm looking at that picture and I can't even begin to imagine how many things are in that. So I don't have any concept whatsoever.
I know. You love a big number.
And I mean, I still have this ridiculous idea in the back of my head of astronomers pointing at things and going, let's look at that one. Like, there's a planet. Let's look at it. No, we have computers and increasingly AI, which can do huge amounts of data processing for us on massive scale. So haven't got the foggiest. I couldn't even get within orders of magnitude. So just tell me.
About 10 billion sources expected
good. That's quite a lot.
To fall out of this. Yeah. Of which we're expecting maybe 1 billion lensing sources.
Right.
And maybe about 30 million galaxies that we get a redshift.
That's a lot. It's a lot of data.
It's quite a few.
Good.
Right, here we go. We actually haven't mentioned this yet, but you mentioned it before we started recording. We've got a 600 megapixel camera.
Mm-hmm. Which is a lot of megapixels, right? My phone has one of the latest phone cameras on the back of it, and that's 48 megapixels. And even then, doesn't tend to do a lot with the 48. It tends to sort of aggregate them together down to small. So 600,
quite a few.
Quite the camera.
So what do you think over, you can answer this a couple of ways. I've got it in a couple of different formats. You can either have a crack at how much data, raw image data that Euclid's going to process over the 6 years. Or equally, if you want, we can have a go at the download rate.
Oh, jeez. I mean, how much data? Like, we're talking like huge numbers of terabytes, I'm guessing.
Keep going.
Like, what's beyond tera? Exa? Petabytes. That's a lot.
So we're looking at maybe 170 petabytes of images.
Now, this relates to part B of your question, of your stat attack question, which is the data transfer rate, because it's not like you can just go and plug it in and download it over a cable.
No.
Like, this thing's a long way away.
It is a very long way away.
So how the hell does that work? Like, I can't even get really big videos off my phone quickly. So how the hell does that work?
Well, we're going to be downloading data from Euclid at maybe around about 74 megabits per second.
74 megabits? That's not that fast.
Well,
I mean, in terms of home broadband.
I struggle to get over about, I don't know, 5. megabits per second from my Wi-Fi is terrible.
You're living in the wrong part of York. Yeah.
I struggle to get over 1, to be honest, on some days. So to me, 74 would be amazing.
Yeah, I mean, look, 74, depending on where you are in the world, is moderately good broadband. Gigabit is becoming more and more standard with home fiber and so on.
Yeah, but that's with a...
that's with a fiber connection to the thing.
House,
there's no
fiber connection.
Don't get
to
me
L2.
wrong. That's pretty good for something which is out at L2, right?
It's about 2 to 3 times better than JWST, and until now, JWST held the record for the biggest downloadableness of data outside the Earth-Moon system.
I mean, don't get me wrong, right? It's fast even by rubbish UK home broadband connection standards. But we're also talking about petabytes of data. Like, this is not downloading a movie.
Well,
this is...
You can watch Netflix from L2. I love it.
That is actually pretty impressive.
Yeah.
Wow.
You could probably watch several Netflix programs at the same time.
I mean, let's not get too ambitious. One would do. So on the one hand, it's amazing they can do it at all. On the other hand, I'm guessing that link would have to be going pretty much 24/7 in order to get all that data down.
It probably depends on the orientation of the spacecraft, because typically, I haven't looked at the specifics for Euclid, but typically you'd be having downlink periods where the spacecraft turns around and orients its pointer to point the data.
Okay.
I'm obviously a space scientist here.
Maybe not 24/7, but
it's going to be a lot. Yeah,
to get
some of that
petabytes of
processing
data
does
over
happen on board the spacecraft. So, and that happens with a lot of modern space telescopes. Actually, a lot of the pre-processing is done on board to reduce the size of the data, so it can come down to Earth.
It makes sense. They put the Instagram filters on it already and then send it down ready to upload. Yeah, it makes sense.
It's exciting, isn't it?
Makes sense.
So, so when can you get your sticky paws on these wonderful data? So we're looking at 3 public data releases. So it's nice. ESA and NASA do have similar policies. In fact, I should have mentioned NASA does have a little bit of a paw in this one as well.
Right. I mean, that's fairly common these days, though, right? Like, everything is everyone.
Yeah. So
this is
NASA
primarily
did develop
ESA, but
some of the
NASA's
technology that's on board as well. So in line with that, there's going to be 3 data releases. The first one we can expect in about 2 years' time. So that'll be kind of like the first couple of years of data, which is very exciting.
So watch this space. I mean, it's ambitious. It's got big plans for a little spacecraft. And
it's no longer called space, which is
even better. Which is even better. It is Euclid, which we like. Yeah. Well, that brings us to the end of another edition of the Syzygy podcast. It's good to be back. Good to be back doing this thing again, reminding ourselves of how to do it.
I think we figured it out.
I think so. Am I right in thinking I had a look at the Euclid webpage before I arrived here today? I did minimal background research on what we were going to be talking about, but it looks quite familiar. The shape of the spacecraft. It looks quite a lot like something that we've seen before.
It looks a lot like Kepler, I thought.
Yeah. And I mean, in the sense that it's a long barrel-y thing, it's not that dissimilar to Hubble. But yeah, I was struck by how much it looked like Kepler. But I guess there's only so many ways that you can build a big telescopy thing.
Well,
in
it's
space.
it's a
having said
thing,
that,
right?
JWST ain't that.
Well, exactly.
Right? This is a very different thing.
This is the old kind of, not old, but this is the other kind of model. JWST had the big folding out gold mirrors.
Yeah.
It just broke every rule that there was to building a telescope.
It's amazing that it even worked at all.
Yeah.
I mean, Euclid is sort of the if it ain't broke, don't fix it.
Yeah.
And then JWST just went, hold my beer. We're going to do everything differently. It's amazing. Anyway, good luck, Team Euclid. We look forward to eventually seeing some data out of this thing and presumably within just a couple of years answering all 5 of those big questions.
Yeah, I think so.
And
I'm pleased about
home.
that.
Yeah, it'd be nice. Finally, we'll know.
I'll have to update my lecture slides.
Yeah. Listen, in the meantime, Emily, if people wanted to contact us with their own thoughts about the broad scale structure of the universe or the nature of dark matter, dark energy, that kind of thing, how do people get in touch with us here on the show?
Well, our hub or our home is our webpage, which is syzygy.fm, syzygy.fm.
That's right.
Easy peasy.
Go there and you can find all sorts of stuff. All of the past 109 episodes. This is episode 110. All the details of those, you can listen to them to your heart's content. But you can also find a page where we have all of our supporters and people who've helped us out on the show. You can find a contact page, most importantly, where you can fill in all your details and send us your thoughts, send us your questions, send us your ideas. And you never know, like episode 109 and various others that came before it, we might even devote an entire episode to your thoughts and questions. That'd be fun.
Yeah.
Where else
You can
are
also
we?
find notebooks on there.
That's true, actually. Yeah, on the webpage, you can go and find the merch store. We can find all sorts of things.
Wonderful.
From notebooks, T-shirts, the works. I one day hope to see someone wandering around in a Syzygy T-shirt. That would be awesome. Someone that I haven't given it to. Which, that would be less fun. Yeah. Where else are we on the web? Are we on the web?
No, we're not. Yeah, of course we have a Facebook.
We do.
You stick the Syzygy thing into the searchy bar thing.
Does anyone understand how Facebook works? I don't know that anyone
I don't think
understands,
Facebook understands how
you
Facebook
can figure it
works.
out. It's out there somewhere. You can find us.
Yep. You can also find us on Instagram.
We are on the Instas.
Yep.
Yep. And now that we are back recording again, of course, we'll be starting to fill these things back up with content. We've been a bit quiet for a while. We know, but we're back again, which is great.
Yeah.
Listen, if you want to support the show, there are a bunch of different ways you can do that. The best way is to just tell everyone. Tell people that you know that there's this fabulous thing called Syzygy and it's full of amazing astronomical goodness and you should listen to it. Go to syzygy.fm. The other way is if you wanted to help us keep the electrons flowing through the website. These things aren't free, And we hope increasingly in the future, as we have in the distant past, in the before times, it'd be kind of nice to do some live gigs and events and that sort of thing.
Well, as the nights are closing in, I don't know what else we're going to do, Chris.
I know. We're going to run out of this glorious summertime and go into long, dark winter of the soul. And you never know, some live events would be cool. My point is, you can support us in doing that by going to patreon.com/syzygypod, where you can fling a couple of quid our way every month and to just help us do the things that we do. But most importantly, just keep listening. And we'll be back again on some kind of vaguely regular recording schedule in the weeks and months ahead.
Yes, excellent.
Emily, it's been great to be back. It's really good to see you.
See you later.
Catch you again next time. Bye, everybody.